Okay, let's get started. Finally, I brought the book. I bought it when I was in Netherlands. The issue has a lot of plenty of mathematicians, so that he can draw like a Poincare disk like this way. And also, there are many Poincare disks. Not only that, Asia has written lots of interesting figure, like a triple, many things. You can take a look at it. I don't think it's available in China. I went to the Asia's museum in Netherlands and then bought it. So there are lots of famous figures. I think you must have known some of them. You can just take a look at it. You can just circulate during the lecture if you want to. And then so I was a bit slow last time. So let me quickly the course, and I was made some mistake. So Gauss linking number, so given the linking R, so which is the embedding of S1 cross S1 inside R3, or maybe sometime in S4. Then so linking number is defined like this way. So linking number is mapping degree of S1 cross S2, where S2 is defined by let's say P and Q is mapped to P minus Q divided by P minus Q. So that's how you define F. So namely, so given a point, 2 point, P minus Q is this vector. Okay? This is P minus Q vector. And take the absolute value. That will define the S2 inside S2, and then the number is the mapping degree of this one. And since volume form of S2, and this is volume form of S2. So we already know volume form of S2, which is something like epsilon ijk xi dxj, which dxk. And the pullback will be written like this way, okay? So which I missed last time. Okay. And then you can integrate over the k1 and k2. And this is equivalent to the energy that costs to move around the magnetic monopole when the electric current going around one of the link components. Once you have the electric current, there's a magnetic field. Is by Beer's-Bott theorem, magnetic field is generated. So therefore, if you try to move along the magnetic monopole, it costs energy. So that the energy cost is indeed in linking number. So since it's topological number, even if you change you deform a little bit like this way, okay? Deform the link like this way. Even though magnetic field is a bit different, the total energy that costs to move along is topological quantity. So even if you deform a little bit, without cutting and gluing, the energy is indeed. So this will be also about. I always. can be just, this is not written in the lecture note. By the way, I have updated the lecture note, so you should take a look at the updated one in e-learning. So this is positive number. So epsilon is positive number, and then epsilon, this crossing is negative crossing. It's a positive crossing, negative crossing. And then linking number is indeed K1, K2 is equal to sum of crossing of epsilon in one part. This is one. So this is another definition of linking number. So for instance, if you look at the upstairs, you have, okay, so the upstairs we have, okay, so I think it's better to write a bit bigger. So the above picture is something like this way. Okay, so this is the above picture, and if you look at the local crossing here, local crossing here, then you can easily see this is this part is exactly the same as this one, okay? Positive, and also this part is exactly the same as this one. So +1 and +1 and divided by 1/2. So therefore, this linking number of this one is indeed 1. So without performing integral, one can just obtain the linking number by just looking at the crossing locally. And then lecture note I have written down, for instance, the something a bit complicated. Let me draw in that case. I mean, I don't know. I'm not that good at the drawing so much. I'm not as sure. Let's see. Yeah. For instance, you can just consider such a linking. Even though linking number is not so strong linking number, link invariance. It's called link invariance. The primitive invariance of link, yeah, the important one. And then this, which was first found by Gauss by a study of electromagnetism, and this linking number of this guy, even though it's linked, its linking number is indeed 0. You can just do that each crossing. So you can just take a look at this one, this bird, and this bird, and this bird, and this bird, and this bird. Sorry. Crossing. I think we shouldn't include it's let me think. I don't think we should include this one. Sorry. It's self-linking, so sorry. We should include only this part. So they cancel each other. Positive and negative crossing cancel each other. And it becomes 0. This linking number is interpreted in late 80s, so-called abelian Chern-Simons by Polyakov, famous physicist Polyakov. Abelian Chern-Simons, late 80s, 1980s, and then after right after the Witten used the non-abelian Chern-Simon theory to and non-abelian Chern-Simon. If you use non-abelian Chern-Simon theory to interpret this linking increments, you will get the so-called Jones monomial. So this is actually indeed a bit more classical. Abelian, you can interpret abelian Chern-Simons, but if you use non-abelian Chern-Simons, it becomes the Jones polynomial. You might have heard of them. So it's a famous work by Whitman. Okay, so that's I didn't cover last time. So let me move on. So let's consider so now, we will go to the so-called left shafts. I don't remember how to spell it. Left shafts, fixed point theorem, and also Poincare left shafts. I think it should be Poincare left shafts, right? Yeah. Poincare Hall. So we are going to using mapping degree. Okay. So let's consider the M is the n-dimensional closed oriented manifold. And you consider some a map. M goes to M. So this is smooth map. With which has isolated fixed point with isolated fixed point. Then we can define. So for instance, there is a manifold, and there is a fixed point. So this point is fixed, but under the map. Okay. So fixed under the map, and then you just consider the neighborhood of this fixed point, this point P, and you consider sphere around them. Okay? So this is fixed point P under the map F, and then one can define the H of Q is equal to Q minus F of P. We do the similar thing. It's usually called Gauss map. We consider similar like this one. So namely, Q is the some very sphere around the fixed point, and point at the sphere. Q is a point at the sphere around the fixed point P. Okay. Oh, what I'm doing? Sorry. You should point me out. So under the F, the point P is a fixed point and also isolated. Okay. Since it's isolated, so therefore around the fixed point, the point will move. Point will definitely move. So this point Q will move to somewhere else. Whatever. F of Q under the map of F. Q is moved to some point F of Q, and if you take absolute value, then it becomes the H is mapped from sphere n-1 dimensional sphere to S n-1. Okay. So this epsilon means it's very small neighborhood around the fixed point. That's what I meant. Okay. And the Q is moved to somewhere else. But if you take absolute value, it becomes the point in sphere. Okay, that's what it means. And then, so given that F with isolated fixed point, one can define the map H. Okay, and we just define an index of point P of F is a mapping degree of H. Okay, so we define like this way. We define. Okay. So this is defined mapping as a mapping degree. So it's a sphere to sphere. One can define the mapping degree. So that's called index at the point P. Then this is very similar to what I have explained in the first lecture. First lecture, we consider. Yeah, I think I will consider this. Ponger-Hopf theorem is essentially the oral characteristic is sum of index of P of the some vector field. P is 0 of P. This is Ponger-Hopf theorem. I explained at the first lecture. In the first lecture, given so there is a point here, point which is the 0 at the vector field. And you just consider neighborhood, and you just define how the vector field behaves around it once you rotate the circle around the point P, 0. That's the Ponger-Hopf theorem. We are moving toward this theorem. Okay. So therefore, what we are interested in indeed sum of index of P of F. P is the isolated fixed point. Okay. The question is, what's this quantity? What's this quantity? Okay. So it's very similar, right? So and indeed, this quantity is indeed the so-called Lefschetz number. So given the F, given the F is a smooth map that will induce the homomorphism between homology itself. Okay? So that's we've already learned in the previous lectures. Given a smooth map, that induce homomorphism. And then so homomorphism. So this is vector space. If you take R coefficient, it's just a vector space. It's some R to some power. R to some power. Let's go K, maybe 2R to K. It's a linear map. Okay? It's a linear map. So you can consider as some matrix. This F star is K by K matrix. So therefore, one can define in alternative sum of trace. Let's go alternative sum of trace of F star. So I means you just restrict the ith homology group. So this F star can be understood as a matrix, because if you set this fix some homology degree, so I is just some R to some power. So it's some matrix. You can take trace and take alternative sum. It's like an order characteristic. Okay. Then this is called Lefschetz number. And indeed, Lefschetz theorem said this one hold. This is Lefschetz fixed point theorem. It's indeed very deep theorem. Very deep theorem in topology. And then this can be understood as an intersection number. Indeed, I want to have an eraser, better eraser. So given that map F, one can define so-called graph of F. As I mentioned, graph of F is the f of x of m cross n. So this is graph. It's called graph of F. So namely, so you just consider the product space of m cross n, and the diagonal element. But this map F will give you some configuration inside the product space, for instance. So this one is, so this, how to say, the diagonal element is just identity map. M goes to M. This point is mapped to just identity. Okay, identity, graph of identity map is a diagonal. Okay. However, so if you have a non-trivial F, you have something. For instance, if this point is mapped to this point, you start with here. And if this point is mapped to somewhere whatever, this point in M, so you have whatever configuration like this. So this is graph of F. If it is not identity. And this is in diagonal element the graph of identity. And Lefschetz number indeed has, so since is indeed given by intersection number of gamma f dot gamma ID. So this definition, if you interpret this definition in terms of intersection number inside M cross M, so this is the you can interpret intersection number, and then this intersection number indeed you just look at. So this point is what? This is a fixed point under F. Okay, so it doesn't change. And the intersection number is indeed, you just consider the sum of all. So this intersection number is indeed the sum over fixed point. Index of P of this F, and the P is fixed point. That's very intuitively correct, right? At this point, they intersect. At the fixed point of F, they intersect. And then we just count by intersection number at each point. For instance, you guys are doing homework, right? If it is complex word, you can just homotopically identify the around here. If it is two-dimensional, real two-dimensional around here, homotopically identify like this, and you just count the intersection number, or like mapping degree H. Okay, this H will give you index at each point. Okay, how the sphere is mapped to sphere. When n, so I'm talking about n is equal to 3 now. Indeed, n equal to 3, S2 is mapped to S2. That can be homotopically classified by this. Anyway, so I think most of you guys already started doing the homework, and then some of them have already submitted. Okay, anyway. So that's the intersection number. And if you use, so given a smooth manifold M, so let's try to connect Ponger-Hopf theorem. So this is very similar to this one, right? Already, it's very similar to this one. Okay. So let's consider the vector field inside M. That will give you smooth vector field, and that will give you so-called flow generated by X. Okay. And phi t equal to 0 is just identity map. Okay, identity map. And then identity map, and you have if has okay fixed point. So this is flow is diffeomorphism. Phi t. Okay, sorry, I think maybe fixed point of phi t, which is a diffeomorphism, is indeed equal to 0 of vector field X. Okay? fixed point of this homomorphism is indeed 0 of the so for instance, if you have sphere, in the first lecture I have written down like how to say downward multiple whatever whatever downward gradient flow of height function, and of course the fixed point is north and south pole, and they are fixed under the flow. Okay, and everything's mapped to downwards. Like if you do that graphically, look at the flow. But the fixed points are north and south pole, okay, of this under the flow. That is a 0 of the vector field. So therefore, index of the, it's very similar to this one, right? So here you also have some of crossing. You can just localize to the some particular configuration to look at the global structure. Do you understand what I mean? Everything that connects local to global. That's what we are doing now. So here, even here, this Lefschetz theorem. So this is local information. You just look at the fixed point of some map. Will give you the global information. Global information. This intersection number is global information of this F. Like this way, so therefore index of P of X is indeed index of P of phi T. This right hand side is defined in this way. You just look at the fixed point and just look at the mapping degree of sphere, rather fixed. And then, of course, Lefschetz number Ft. Okay, this is the homotopic to identity. So this is homotopic to identity. So the map, if it is homotopic identity, this is equal to trace of minus 1 to the identity map of Hi goes to Hi, trace of identity map of Hi to Hi. What is the dimension of identity map? Sorry, trace. What is the trace of identity map in this case? So dimension of homology. This is dimension of homology group. I'm using identity map. Sorry, it's a mistake. And then, therefore, this is indeed dimension of homology group. Okay, R coefficient. I'm working on R coefficient. Okay, therefore this is equal to order characteristic. So here I use the fact that if they are homotopically equivalent, they will induce the same homomorphism under the. So given that F and G are homotopic, F star is equal to G star to M homology group of M. In general, M goes to M. Homology group. Homomorphism is isomorphic. That's what we have used. So since identity map, the flow is homotopically equivalent, homotopic to identity map. Sorry, I think T equal to 0. I think I should T equal 0, which is identity map. Sorry, this is the correct expression. Okay. So then Lefschetz theorem tells us that this is equal to sum of index of X, P is 0. Okay? So this is Lefschetz theorem. So Lefschetz number is sum over all the index at the point P, fixed point. Now on the other hand, if you use homotopy, that Lefschetz number can be connected to order characteristic. This is exactly what I have written over there. So this is called Von Hoff theorem. So here you also have some. So here this one is local information, local. But this is global topological information, or N. So now Poincare theorem, Hop, and also this left-shift fixed point theorem in general, more generally, will connect local information of the manifold to the global information. Connect. Try to extract global information out of local information. So the people just call it slogan local to global. So that's many people topology and geometry. Working on topology and geometry. This is a slogan people have. And Poincare theorem is a salient example of that connects local to global. Okay, this is a point I would like to reach last time, but I was too slow. Sorry. Let's talk about fundamental group. So we learn homology, but another important algebraic topology invariant is called fundamental group. Okay. More generally, homotopy group. But I'm not going to talk about so much about homotopy group. Let me go on the fundamental group. So now it's everything M is a topological space. So given a topological space M, and pick a point x0 and x1. So the map between I to M assumes the continuous map I to M such that this gamma 0 is x0 and gamma 1 is x1. It's just a map, whatever map, from x to x0 to x1. Okay. So this is called path. On the other hand, smooth path, or just continuous map. It's a topological space. It's just continuous. You don't have a notion of smooth. And on the other hand, one can just also introduce so-called loop. As you can easily imagine, loop is something like this one. So that the I loop is let's go gamma tilde. I goes to M such that the gamma tilde naught is x naught is equal to gamma tilde 1. And then what Poincare introduces is a very, very simple thing, but very important. So what Poincare introduces is that so fundamental group is denoted by usually pi 1 M and x naught. So this is called base point. Base point. So this is indeed, so this is group. So as a set, it's a homotopy classes of loops. Based at, so this is loop based, this is called loop based at x naught. Based at x naught as a set with a group structure, such that gamma naught times gamma 1 is equal to gamma naught dot gamma 1. So this is the, and also gamma inverse is equal to gamma inverse. It's very trivial thing. And the identity element is just constant map. Constant map. So this is group structure. Okay. Let me explain what it means. Let me explain. It's a very simple thing. It's a very simple thing, but I just write down a word. It looks complicated. It's just very simple. So, given a manifold, whatever manifold, and base, you just pick base point x naught, and then you just consider gamma naught with orientation. Let's go gamma naught, and then gamma 1. The homotopy class means that you can deform this path continuously. Therefore, this gamma naught is a okay. So let's so this gamma naught homotopy. This is called the representative of. I mean, as I mentioned, homotopy is the equivalence. Homotopy equivalence is the equivalence class. So you have to pick representation. Okay, representative, which means that you can deform homotopy by paths. Like let's call this is gamma theorem. Did you say blue is hard to take? Okay, I think I should. Okay. So, by homotopy means you can just deform by homotopy. Okay? Homotopy is that let's go gamma such that the I cross I goes to M such that the let's go gamma 0 T is equal to gamma naught T, and then gamma 1 T is equal to gamma naught tilde T. Okay? That's a homotopy. Okay? So therefore, this yellow line is a deformation in the first I. Okay? First I, 0 to 1. At the 0, you have an orange curve. At the 1, at time 1, you have a blue line, and then this yellow is a deformation. So therefore, this as a representative, so it's independent, so it's an equivalence class. So therefore, you can pick whatever representative. Wow, it's hard to pronounce. Representative gamma naught or gamma tilde. So okay, so that's so you just look at the equivalence class, and then multiplication as a group is just if you have gamma naught dot gamma 1 is indeed the same as you just consider two map like this way. So therefore this is homotopically equivalent to, let me erase in the middle, homotopically equivalent to this map. Okay. So let me. So this gamma naught and gamma 1, if you take a product, homotopically equivalent to this yellow one. Okay. So this is gamma. Let's go gamma 3. So this is gamma 3. here upstairs gamma naught is just composed as a map, okay? As a map. So you just divide segment I in the middle way, in the middle. So this is I, 0, 1/2, 1, and this part is mapped to use to M by gamma naught, and this part is mapped to gamma 1. Okay, that's a composition means. Okay. Do you understand what I mean? So this part is mapped to this first orange line, and the second one is mapped to this gamma 1 orange line. Okay. And that is homotopically equivalent to this yellow line. Okay, yellow. That you can see. So that will give you group structure. And the question is, what is the inverse? Gamma naught, gamma inverse is indeed. Now you just take the orientation. So the gamma. So that's gamma naught inverse is just take the opposite orientation. Okay. So you just take opposite orientation is the gamma naught inverse. In other words, if instead of 0 to 1, you just take 1 to 0. Okay, that is the inverse. Okay, and the identity is just map all the segment into the base point. Okay, base point. That is identity map. Everything homotopically equivalent. So therefore, identity map can be something like this one. You can shrink to the point, right? If there is no loop, there is no like how to say genus or whatever. If it is contractible to the point, it's just identity inside a fundamental group. That's a fundamental group. Okay, good. So, unlike homology group, the homology group, whatever ring we use, homology group of I, M, and then whatever for R, ring R. This can be Z or R, or sometimes Z to be some M or so on. Everything, this is a abelian group. It's a abelian group. Abelian means in commute. Okay? So for instance, if it is Z is abelian group, right? A plus B is equal to B plus A. This is abelian. So even if you swap. But fundamental group in general is non-abelian. It's non-abelian group. By the way, usually it's independent of choice of base point. Even if you change the base point, you can connect. So change x0, x1, pi 1 of element xm, x0, and pi 1 of m, x1. Always, if you have a loop around x0 here, you can always connect x0 to x1, and so that you can start with x1 and go back, take the element of the fundamental group in the here, and then go back to the x1. So you can just always one-to-one, isomorphism as a group. So it's independent of the choice of base point. So usually people just write down without base point. It's a non-abelian group. Let me show you. So for instance, let's consider R2. Get rid of 2 point. So just get rid of 2 points. And then take call it this one is A, and also I call it this one is B. So in R, I just get rid of 2 points. Okay? So these are homotopically inequivalent to two elements. Okay? Two element, two loop. And then, so this A times B, let's see, it's not the same as B times A. It's not the same as B times A. They are not homotopically equivalent. So A times B, let me think. A times B is something like, something like this way, right? You just go like this way. On the other hand, B times A is something like and they cannot deform, this white line, white curve cannot be continuously deformed to blue curve. So you can easily check. So therefore, the group structure like this way, if you go A and B, I think I should write down. So, if you look at group structure, let's consider A direction is this direction, B direction is just pictorially depict the group structure of the group. So you just go to A direction, this one, and you can go to B, this one, or this way. So this is A, and this is B, and if this point is A times B. A times B. And this is A times B inverse. Okay? And so on. So this pictorial, so this point is something like A square. Just go 2 times A square. And so on. And then it becomes really, so therefore A times B is not the same as B times A. So this is B times A. So this is B times A. So this is B A. So B times A. Okay, B times A is not the same as B, A times B. Okay? So therefore they are non-commutative or non-abelian. Okay? It's called non-commutative or non-abelian. And then usually it becomes so-called Kelly graph. It's called Kelly graph, and then you have something like it's more like fractal structure. That's written in lecture note. So the group structure is really look like this. Kelly graph. So once you take B A B A and so on, B A B A A B A B. So that means that means that since A times B is not equal to B times A, so you have to take like infinite, like a tree at each intersection. You have at each intersection you have a crossing like this way, and then that will form like a fractal structure. That is called Kelly graph. I cannot draw nicely here, so that's written in the lecture note. This is called Kelly graph. Kelly graph, and then this is the Kelly graph is the pictorial picture of fundamental group of the 2-point group. So it's homotopically So it's homotopically equivalent to the S1 with S1 with the point is identified. Okay, that's usually write down this. So S1, how to say, check S1, homotopically equivalent to. So okay, so maybe I should write down or pi 1 R 2-point image is homotopically identified. Homotopy equivalent to the S1 times 2 copy of S1, but the 1 point is identified. That's okay. But sometimes if you're very, very lucky, it can be abelian. For instance, if you consider torus, as I mentioned, torus fundamental group is something like, so if you have a torus, fundamental group is, this is non-trivial cycle, and the non-trivial cycle. So you have two non-trivial elements. So usually people call A cycle and B cycle. B cycle, A cycle. I don't remember which one is A cycle or which one was B cycle. But anyway. So in the homework, did you maybe I wrote the H1 of T2 is equal to maybe Z coefficient and Z plus Z. Okay. So that this Z is spanned by this A and this Z is spanned by B cycle. Okay. And then if you write down fundamental group, usually people just write down it's called it's called I think word and it's called word and relation. Relation is A, B, A inverse, B inverse is trivial. Okay? A, B, A inverse, B inverse trivial. So people just write down A, B, A inverse, B inverse. That's how people like this. So this relation means trivial. It just stands for trivial element. So therefore, trivial means AB, A inverse, B inverse is equal to identity. So this will give you AB is equal to BA. So it's a committed. A and B are committed. Okay. It's a commute. So therefore, indeed, this stands for Z plus Z. So magically, in the fundamental group of T2, it becomes abelian. Whereas this fundamental group of R2 mod 2 points are non-abelian. A times B is not equal to B times A. So, and usually people just, this one is called the free group. Z star cross Z star, and this is equal to AB, and without no relation. Without no relation means the really AB is not equal to BA, and you just consider whatever A, B, whatever. You can take also inverse. Let's go inverse, whatever. All the elements are written like this way. And so on. You just write down all the, how to say, product. So for instance, this is the A square and B, A, B inverse, A cube, and B minus 2, and A and B to the 4th, and so on. Okay. So there's no relation. You cannot exchange B and A. Okay. You cannot, because of non-commutativity. That's called free group. This is called free group. usually people write like Z star plus Z star. Z, how to say? Z star Z. It's just a free group generated by two elements A and B. And this torus case is very special. Somehow it becomes commutative, but it's very special case. And torus case is fundamental group, and the first homology group becomes isomorphic. But it's a very special case. Usually, almost all example, fundamental group is non-commutative. That you see in homework. Okay. And then, again, like homology group, so given if you define some topological quantity, so you just consider how it behaves under the map. Okay, so given the map F n, and you just consider x naught is mapped to F x naught, then this will induce, so let's see, so it's a smooth map between manifold. Let me write a bit more differently. N to n, and at the one point you just consider fundamental group, whatever fundamental group at point x naught. Okay, and that is mapped, x naught is mapped to some point f of x naught. Okay. So under the smooth map f or continuous map f. And sometimes this loop is mapped to some contractible cycle like this. Sometimes non-trivial loop is mapped to some other non-trivial cycle like this way. Okay? But it just the map is just you can compose I is mapped to some loop here, and that is mapped to f but to the n, okay, to the loop. Therefore, naturally induce f star is induce the pi 1 to m x naught to pi 1 to m f of x naught. Homomorphism as a group. Homomorphism. It's just composition. So you just segment is mapped to the loop inside of M, and that is mapped to the loop in the inside of M. Okay. So that is the after homology equivalence. Okay. And as you can easily see, so since we consider the homotopy equivalence of loop, indeed, if M and N are homotopy equivalence, then F star of pi 1 and x naught is indeed isomorphic. That can be easily see. I think, for instance, if you consider the R, it's a very simple exercise. R2 mod point. So R2 more point is homotopically equivalent to what? S1. Good. S1. So this point here removed inside R2, then you can have the unit circle around the point removed, and then everything x is shrinks to the point x goes to take the unit vector. Okay, this is called deformation retract indeed. Because so this is called R2 point is deformation retract of S1 to S1. More precisely, usually if M is deformation related to M, usually you have an inclusion map. Moreover, it's a subspace, so therefore N can be understood as a subspace. Okay, inclusion, or maybe I should subspace. The subspace such that the F I M cross M such that the F0 X is just identity map. Whereas the F E of X is included by M, and then Ft of F1. Ft of Y is equal to Y if Y is inside. So this is deformation retract. So namely, if so here, as you can see, when t is equal to 0, it's just identity map. T equals 0 is just identity map. But when t equal to 1, everything retract to the circle, right? S. Now its circle is M. So everything, all the point in X, any point X, maybe any point X, any point in M is retract to the M. Okay? Everything's at the end of the time t equal to 1, everything is included M. Okay? Everything is included M. And if you restrict the space Y inside a point M, so namely point on this circle, everything identity, it doesn't move under the homology. It just stays the same. That's what it means. That's called deformation retract. Everything just deformation retract to the subspace M. That's what it means. So therefore, fundamental group of R2 mod point is the isomorphic to the fundamental group of S1. What is the fundamental group of S1? Z. Good. So you just count how many times you just rotate. Okay? This is Z. Okay. So therefore, the fundamental group is also invariant up to homotopy. If you have a homotopy equivalence, you have a same fundamental group. The same here. R2 more point. So this is also one example of abelian group. It's a very special case. Usually only like S1 cross S1 cross dot 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 cross S1, you have fundamental group sublinear. Okay. So this will give Z plus, Z plus, Z plus, and so on. As you can easily guess in a fundamental group. But okay, and then as we have seen, so if you get rid of 2 points, it's the same as 2 copy of S1 identified point. This one's the S1 wedge. It's not wedge, it's called check. Check S1. It's a homotopically equivalent, and this is a free group of this pi 1 of this S1, check S1 is free group, which is not needed. What is the fundamental group of Sn? N greater than 1. What is the fundamental group? Yeah. Pi 1 of S n minus 1 is trivial. Usually trivial in fundamental group is usually group with non-abelian group. So usually write down the product. A, B is a product. B is not equal to BA usually. So if you use the 0, I mean, presumably you assume like an additive structure. So usually people just write trivial. Come on, it's trivial. So that you can easily see, right? So given the sphere Sn, whatever group you have, maybe it's a bit annoying. So let me erase. So given a sphere, and then you have whatever loop inside a sphere, whatever loop. You can pick the point that is not included in this loop. You just get rid of the one point. So Sn mod point is homotopically equivalent to what? Huh? What? Say it again. Say that again. You just, given a sphere, n-dimensional sphere, just get rid of point. Right? Is that deformation to retract to the point? This deformation retract to the point out of homotopy. They are homotopy equivalent to the point. So if you get rid of the point, you can always do that. I mean, it's just, measure, it's called measure 0, whatever. It's a circle inside a sphere, or whatever, loop inside a sphere. You can always pick a point that is not include this yellow curve. Okay? And just get rid of the point, and that is deformation retract to the point. Okay? That is deformation retract to the point. So therefore, fundamental group of the sphere, which is which is greater than 1, is trivial. You cannot do that if you have n is equal to 1. N equal to 1, you cannot get rid of point, but without touching the loop. If you circle, you have a fundamental, non-trivial fundamental, you cannot pick the point. That is not on the loop. That's the difference. So the fundamental group knows distinguish n equal to 1 or otherwise. Okay, so, and in particular, the fundamental group is trivial. If fundamental group is trivial, n is called simply connected. simply connected. Here is one example. Okay. By the way, okay. So now, simply connected. So for instance, sphere is simply connected. Rn is simply connected. Of course, point is simply connected. And so on. Oh, by the way, I think it's better. So let's consider covering space. So covering space. And let's see. So let's consider covering until is called covering space if you pick for any x in M exists the neighborhood that contain x such that let's go this is called P inverse of U. If you consider U is a bunch of copies of U's. So namely, so if you have a space M and a pick point X, and then there is a neighborhood U, and this is M, and M tilde is upstairs somehow, and a projection or covering map, and you can just take neighborhood around here. That's what we call U. And if you look at the pre-image of under this map, you have a bunch of copy of this neighborhood, many copies. This is called covering. Okay. To be honest, differential 9.8, I don't understand why I put this one. I see. I think it just differential 9.8 is a precise statement of what I said here. But I think I don't want to get into the detail. So just give you an example. So let's consider S1 cross S1 is just a map to the okay. So this is the example of covering map. So the covering map. So let's consider the circle here. And in the pre-image, if you look at the pre-image, you have pre-image of 1. So if you, so let's call this is P. Pre-image P inverse of 1 is indeed is called nth root of unity. E to the k so okay, let's use 2 pi I say 2 pi I n say. Then what we have is 2 pi k I theta over n. Pre-image is always like this. Is it okay? Where k is equal rounds for 0 to n minus 1. Some integer between. As primitive k is relative unity. So in other words, you have a circle, you have whatever. So this is eighth root of unity. Eighth root of unity. So this is e to the 2 pi I over 8. Sorry, I don't need to say it. And so on. So therefore, the covering map, roughly speaking, is mapped like this way, n times, okay, like this way. So this point is identified with this point. Okay. They are identified. And if you look at the neighborhood, here, and if you're sufficiently small, if you pick a point, if you're sufficiently small, then the pre-image is something like this one. Okay. And copy of and if it is not sufficiently small, if you take the circle, it becomes connected, everything connected. So you cannot do that. So you have to take sufficient small neighborhood. Okay, that's a covering map. Okay, so and then let me move on. Universal covering. Good. Today my condition is better than last time. So universal covering is universal covering is that the of M is that the M tilde M. This is covering map. Such that I1 M is trigger. Sorry, M tilde. So M tilde is simply connected. That's called universal covering. What is the universal covering of S1? What is the universal covering of S1? Huh? What is the universal covering of S1? What is the universal covering S1? Given S1, okay, do the forever, okay, covering forever. Since R is simply connected, it's a universal covering. So given a R, and just do the integer or whatever. And 3 and 4, okay. And you just identify this integer point, okay. You just identify integer point. You will get the S1. So usually, as you know, this R is contractible to a point. Okay. So the pi 1 of R is a trivial. And furthermore, it's covering map to S1. Okay. And what is the pi 1 of S1? What is the Z? Okay. So usually, so this universal cover R or Z, people just write that as one as a quotient space. Z is a fundamental group. This is fundamental group of S1. You just quotient space is you just identify all the integer points. What you end up with S1. Okay. And this Z will give you indeed the pi 1 of the S1. Moreover, I can just give you another example of the universal covering. So then let me stop for the break. Let me give you the last example of the universal covering. So if you consider S1 check S1, so this is S1 plus S1. Fundamental group is free group. In lecture note, I just write down like this way. I think correction of free group of A and B. And then what is the universal covering? What is the universal covering of this space? This is very difficult, but I already given an answer. So this is a Kelly graph. All those Kelly graph is indeed will give you universal covering. You understand? So it's indeed a contract. It's tree. Okay, it's tree. So it's a contractible. Okay, but given a fundamental group, you get some different point, right? Different point indeed. That is will give you. Given a fundamental group, whatever A square, B, A, and so on. A square, B, A, and so on. Given a fundamental group element here, you can pick one point. It's the same thing here. Given a fundamental group Z, right? Given the fundamental group Z, pick some point in N. So you can just always pick the point in the universal covering space and integer. The same thing happens here. Given the element in fundamental group, you can always pick some point inside a Kelly group. And also it's contractible. That's a universal covering of this S1 check S1. Okay, so let's take a break. So yeah, I think Escher's book, I brought Escher's book, and I think the book was go this way and here, and you should bring it to the other. if it is R2, I think what you mean is so this is two-dimensional, right? It is one-dimensional. So one-dimensional means the let's see. So we need this condition. Its pre-image of the neighborhood is always the bunch of copy of this. So therefore, if you look at the S1, check S1. If you look at this point, and the neighborhood is always one-dimensional. One-dimensional. So its pre-image has to be also one-dimensional. If you pick this point, it's almost like a, how to say, it's like a, it just crops, right? If you pick this point, neighborhood. Therefore, also pre-image has to be a bunch of copy across. So therefore, if Kelly graph satisfy this condition, so if you pick this point, you can just pick around here, around this point. If you pick this point, you can just pick around this point. But if it is if R2 is just a two-dimensional R2 is two-dimensional surface. And if you look at pre-image, it's hard to take. I mean, it becomes two-dimensional. It becomes two-dimensional if you pick it. Therefore, they are not the homomorphic. That's why you cannot take R2 as a cover. Oh, by the way, I decided not to give the answer to the bonus problem. So you should think by yourself. But I mean, you guys saw the reason why I give you the how to say, the Klein bottle to compute homology Klein bottle. This is S1. So this Klein bottle is the S1 cross I. Right? This is the case. This is Klein bottom. And the bonus problem, I just ask you to do the replace S1 to S2. Do you understand what I mean? Klein bottom is just you have a I times S1. And more precisely, this is I and S1 and S1, and top and bottom is identified the opposite way. That is X and X index. It's an antipodal. And it just generalizes to this one to S2. That's the bonus problem. So if you can compute the homology group of S, the Klein bottom, you should be able to compute indeed the bonus problem. But I'm not going to give you a note. I'm not going to give you. Just think by yourself. Oh, by the way, so somebody asked me to join some tomorrow, not tomorrow, on Saturday, some meeting in Jangwon. I already forgot, some like a undergraduate students meeting. Are you the one? I think this Saturday I have to go to Jangwon, like 3 p.m. Where? Where? Okay. What should I do? I don't know anything about. What? Discussion? What kind of discussion? Huh? Okay. And who are coming to that meeting?
Mostly undergraduate students, and would like to learn about how to. Would like to learn about some. It's informal chat.
Informal chat?
Yes.
Okay.
I would like to know how physics work, theoretical physics work.
Okay. Okay. And then
We have some questions about
research, how to perform research and so on?
yeah.
Oh gosh, I don't know. I wish I would like to know that. Okay, let's do that. Let's get started again. Okay, today's good pace. Sorry, last time I was too slow. My differential not good. Anyway. Well, semester is long, sometimes I'm tired, sometimes I'm good. So, but, okay. I'd like to know, who else are coming from faculty members on Saturday? Only me? No. I'd like to know from the other opinion. Okay. Then I don't need to go there. I don't know how to perform research actually. Okay. So another example for fundamental group universal covering is the RPN. So as you can easily see, Sn, RPN is the double covering. And then double covering, so it's just quotient by antipolar map, Sn. So, and this is indeed universal covering. Pi1 of Sn is trivial, as I mentioned, when n greater than 1. So therefore, fundamental group, and then also it's Sn is RPN is a quotient is quotient by antipolar map, which is Z2 action. So people just usually write down Z2. So therefore, what is the fundamental group of RPN? What is the fundamental group of RPN? It's the same. Here you have a universal covering, a quotient by Z, because the fundamental group is Z. So it should be Z2. In the case of, for instance, RP2, it's very easy to see the picture. Given a sphere and a quotient by antipolar map, you just antipolar map between so therefore essentially you have northern hemisphere and southern hemisphere identified. So you have this northern hemisphere. However, you have to be careful about the equator, since this point, this half circle identified opposite a half circle, right? Great equator. Therefore, this point is identified this point. Okay. This yellow line is non-trivial element of pi1. Okay. And if you have two copies of them, then that can shrink to the point. Okay. Along the northern hemisphere. Therefore, this A times A squared is equal to trivial. But A itself is non-trivial. Okay. Therefore, Z2. Yeah. So what is the universal covering of SO3? What is the universal covering of SO3? You guys should have known. Huh? S3 or SU2? Yeah. You did homework, right? The first homework. Do you remember? Okay, since I just explained the same thing in the string theory, let me repeat. So therefore, so this is S3, and this is RP3. Okay, and it's just universal covering. And pi1 or RP3 what? Z2 good. So this Z2, I just did the same explanation in string theory, so that most of you guys know here. So given that so non-trivial element of the this Z2, this A corresponding to A is something like a 2 pi rotation. I really forgot how to. Oh my goodness! How I did that in string theory course? Yeah, this is 2 pi, but once you do the one more 2 pi, you get the original point. So this is 2 pi. You have a non-trivial element. I cannot go back. I feel uncomfortable. But if you do one more 2 pi, if you add one more 2 pi, you get the original. Okay? This is non-trivial element to this A. So you cannot undo that. And also that is inserted non-trivial element in SO3. Okay, SO3. And also another way to see is that so you have 2 pi rotation. So if you do the 2 pi rotation, okay, in the belt and go up and down, you cannot undo the rotation. Okay, but if you start with 4 pi rotation, 1, 2, 3, and 4 pi rotation and go up. Go up and go down. You can undo. So this is really the 2 pi rotation is non-trivial fundamental group inside SO3. And the 4 pi rotation, if you do the 4 pi rotation, you can undo it in the inside of SU2. And usually people, this one is called, another way to call this is spin 3. I'm going to explain the LD group today a little bit. I'm just going to talk about this. Usually pi 1 of SON is indeed Z2. And the universal covering is called spin group. And this is indeed the way you explain this using a belt is first explained by Dirac. That's how Dirac explained the non-trivial fundamental group of SO3, and then if you do the 4 pi, you have a spin group. That's how he explained in the spin group. That's why this is called Dirac's belt trick. So that's how he explained the double covering of spin group to SON. Anyway, so that's how you see non-trivial fundamental group elements. Okay, let me move on. Okay, my throat is really choky. Okay, so let me move on. Yeah, at the end of the lecture, I always make some mistakes, so just be careful because I'm getting tired. Hey. Okay, so homology group. To compute the homology group, we just did some trick, right? So we have M1, M2, whatever, U1 and U2. So M is equal to U1 and U2. So the union of U and U2, and you just consider also whatever. Intersection U1 and U2, this part, and you just H of M can be just considered constructed from A and B cross sequence. That's what we have seen. So this is called ambiguous sequence. And we can do the similar thing for Homology Group. I'm not going to go into detail, but we can do the same thing. As for one comment. I just give a statement. I'm not going to explain anything. I just give you a statement. You can just take a look at Hodge's book if you want. So section 1.2. So I just give you a statement. So about this situation, okay, and also, sorry, UI and also U1, intersection U2 are part of that. Then you just consider normal subgroup. So you just consider normal subgroup. This is called normal subgroup of inside a free group. This is a normal subgroup. Normal subgroup. I'm not. I will briefly explain normal subgroup. Just wait a second. Generated by I1 star omega I2 star omega inverse, where omega is inside I1 and 1 intersection U2. Of course, I1, I is just a inclusion map, intersection U2 to UI. Okay. Then, so then, I1 of M is isomorphic to free group generated by two fundamental group and divided by N. So this is the segment. This is called complex here. What is a normal subgroup? I will explain what a normal subgroup is. Yeah. Normal subgroup is, what is a normal subgroup? Normal subgroup is a group, given a group G, and people just write down normal subgroup. If any N and G is inside G, such that G and G inverse is inside, then it's called normal subgroup, as far as I remember. Hopefully I'm correct. It's called normal subgroup. Okay. Yeah. So yeah, I don't think I want. I have to explain lots of things to explain this one. So I think if you're interested, you can just take a look at the Haja book. I just make a statement. So given that some nice normal subgroup inside this free group, and then you can just have the fundamental group as this free group divided by this normal subgroup. That's the statement of the fund complex theorem. So this is analog of this Vitor's sequence. So you just, if you know the fundamental group of each component, and if you have some data from intersection, one can compute fundamental group of entire space. That's the statement of fund complex theorem. So it's a fundamental group analog of the Meyer-Vitor's sequence. I just give you the simplest, the simple version of fund complex theorem. Simple version is the if above setting, if U1 which U2 is simply connected, then the normal subgroup is trivial. There's the isomorphism pi1 U1, pi1 U2 is isomorphic to pi1 M. So the simple example is indeed this S wedge S, not wedge, S check S. This is 2 copy of S1, and you can take U1 as a circle here. This is U1, and U2 as another circle. U2 is another circle, and the intersection is of course the point here. This is U1 intersects U2, so it's trivial. Okay? Its fundamental group is trivial, it's contractible, so it's simply connected. So therefore, as you can see, so pi1 of S1 check S1 is indeed isomorphic to pi1 of circle free group pi1 of S1, and then this is isomorphic to free group general 2 element. But if this intersection has non-trivial fundamental group, you have to be careful. That's what it means. You have to use some normal subgroup. I'm not going to explain. It's a bit difficult to explain. I have to spend at least 15 minutes to explain everything. So I'm going to skip. And if you're interested, you can just take a look at Hatch's book. Okay. So this is fundamental group, and then let me. Sorry, I think I just put it here. Let's move on. So the reason why I read pi1 of M, and this is related to S1. Okay, the loop is just related to S1, right? And the question is, what is Sk of M? Okay. So this is homology group. Yes. So let's look at the so let's consider I think yeah, okay, so let's look at consider define I to the n is equal to bunch of copier segment. And copier segment, and then we consider alpha I n equals to n such that this is a continuous map, and such that the boundary of I n is equal to is mapped to, and under alpha is indeed x naught. So everything's straight to the point. So what I meant is the given I, and when n is equal to, so this is I cube indeed. It's mapped to some manifold m, and then all the boundary. So I is also you just include inside of this cube, okay? And the boundary of I3 is indeed I3 is indeed really the cube, okay? And this boundary cube is mapped to x naught, but inside a cube can be anywhere, okay? So therefore, people just usually write I3 like this way. In other words, another way to write down this way is Sn and a point x. Let's go y is mapped to n goes to y. So what we have done is essentially given a cube, you just identify the boundary. Okay. If you identify boundary, you get the sphere, right? Can you see that? In some sense, you have this is isomorphic to some ball, or whatever. I cannot draw the picture. The ball, and if you identify the boundary, you get a sphere, okay? Like this way. The reason why I have write down the product and copy of I product, it's easy to see the group structure. So to define, so this is called we call this is a loop based at x naught. Okay. And loop inside M. Oh my goodness, I should erase. Maybe I should go here. So we can just consider the n loop. So the pi n of M is x naught is the homotopy equivalence, homotopy class of n loop. N loops based at x naught in a group with group structure. Alpha star with group structure now is abelian structure such that the alpha star beta is equal to alpha star beta. So schematically, we just consider I times I. So I times I is mapped to some M here. But we just divide I inside the middle, and the half of space is mapped by alpha, the other half of space is mapped by beta, and this middle, you just shrink the point. So in other words, we just write down, so alpha is mapped to some sphere in here. On the other hand, beta is mapped to a sphere like this way. This is an alpha and beta. And this point is really this point here, okay? Or all the point. This yellow point, yellow boundary is mapped to, maybe I should use different color, I guess. Orange, the boundary, and also in the middle line is mapped to the point here. That's how you define the group multiplication. Of course, the identity map. So identity map is indeed the constant map to x naught. Okay, so that's how it works. So identity map, constant map. And then we do this, so alpha inverse is just a, you just alpha inverse and also alpha inverse. It's a bit hard to imagine, but the inverse map is that you just have two copies of alpha and alpha inverse such that you can just undo the rupture. That's how you define the inverse element. And indeed, so unlike the fundamental group, this becomes Hermitian. Oh, by the way, where's the Hachette group? Sorry. Yeah. Okay. I think after that you should bring to this line. After you do that, you should bring it to there. So, I mean, schematic diagram, so indeed, n greater than 1, so then pi n of m becomes abelian or commutative, which means the alpha star beta is equal to beta star alpha. So you can just have alpha and beta, but by homotopy equivalence, you can just have a bit shrink the region a little bit like this way, alpha and beta, and this shaded region is everything mapped to the point, orange point here. Okay, so one can do after homotopy like this way, and then by homotopy you can just swap beta and alpha. At the end of the day, you can just bring it to beta and alpha by after homotopy. So if n is greater than 1, it becomes abelian. And then the example, which is not written in the, what's this? Do you know what this group is? Nth element of Cn. So this is indeed Z. If you look at the 1, fundamental group is Y and Z, right? So you can easily guess. What's this indeed? So this is indeed mapping degree. So given the Sn, Sn, you can just map to Sn, another Sn. Sn, map F. This F is homotopically classified by mapping degree. Okay? So therefore, this part, nth element of fundamental the sphere, Sn is really map. This D is mapping degree, and it's very important to compute Sn. This is a very important problem. It's a kind of advanced topic of the algebra topology, and it's very interesting to study. It's a very it's deep subject that I'm not going to go into detail. To compute this one, and also I'm going to explain Lie group today a little bit, and compute pi of Sun or Un. I'm going to explain what's Un and so on from now. Of On, it has very nice structure. It's called both periodicity. It has very deep structure. Some periodicity in the K. If you're interested, there's a very nice explanation of Miln's Moore theory in last section. It's very beautiful. Milner derived both periodicity by the Moore theory. If you're interested in advanced topic, you can just take a look at the last section. But if you want to go to the last section, you have to read through whole book. But it's a very wonderful book. When I was a student, I read it, and I'm very impressed. And also I met Milner in the Stony Brook. He's now professor in Stony Brook, and then he's very quiet, and he's already legendary. He got a Fields Medal in the 1960. He has been professor at Princeton for decades, working on the revolutionary result in the differential topology, differential geometry, topology, many stuff. Oh, and then I need to explain one thing before going to the and then his lecture differential topology from differential geometry viewpoint. It's a very thin book, and if you go to the YouTube or something, there is some video of the. I think he gave it in front of the audience. I think 60 or 70. I highly recommend you to take a watch. I think 2 or 3 video. I think 60 or 70. He explained elegantly about the topology from differential geometry, different viewpoint. I highly recommend you to do that. I forgot to mention one thing. So that's one is called Poincare conjecture. Now it's not no longer conjecture. Poincare conjecture. Now it's called Perron. It's better not to mention. Okay. So the Poincare made a conjecture. Every simply connected closed n-dimensional manifold is homeomorphic. Very simple statement, but it's hard to prove. This is called Poincare conjecture. when n is greater than 4, it's proven smell. Smell. And the 4, I think this is 1961. He used this so-called cobordin. And n equal to greater than 4, you can just use so-called Whitney trick and so on. So you can do lots of things. So somehow higher dimensional is easier in topology. N equal to 4 is very difficult. Got this one genius called Friedman in 81. I think that's worth remember. 82 was proven by a positive way. This is, and also n equal to 3. So through the systems and geometralization conjecture, proving geometric conjecture, paradigm prove 2003 or something. I really forgot. 2 proven. It's very simple statement. Every simply connected closed n-dimensional manifold orientable. I think. Okay. Yeah. Yeah. So you don't need orientation. If it is non-orientable, you have a double covering. You have a covering map that will give you Z2. So it's E2 in the fundamental group. So this is okay. There is some nice expression again Milner. You can just search Milner and Poincare conjecture. He has a really good exposition of the Poincare conjecture. Okay, so this is the so-called H-cobordism. When I was a student, I tried to read his paper. He has really wide imagination. This paper is hard to read actually. This paper is much more difficult. It's called wire topology. I think, as far as I remember, this wire topology is the culture is given by so-called Bink in University of Texas, Austin. Even now, University of Texas Austin has a nice group on topology, but they developed some very nice how to say, and also it's very very famous by very strict education. When you present something, you cannot look at any note in a textbook. You have to put everything in your mind and present in front of the professor. So it's a very strict culture they develop. And Paraman, they just use so-called system geometrization conjecture. Systems geometrization. And here it's like a rich floor and so on. They use more like a Riemannian geometry or sophisticated Riemannian geometry. Okay, so let me move on to Lie group. Yeah, so there are a lot of application of this homology group to physics. I just written down one example, global SU2 anomaly by Whitman, but I'm not going to explain. You can take a look at it if you're interested. Okay, let's move on to Lie group. So Lie group is very important in the Lie algebra. So Lie group G is a manifold with group structure. Such that some multiplication map is smooth. It's smooth. Smooth map, like a smooth manifold. So this is Lie group. It's very simple definition. They have smooth. And then you can just define left multiplication given the h element h. So you can have a left multiplication such that the g goes to g, such that the g is mapped to hg. Right multiplication is very simple. G goes to gh. So this is right multiplication. So this is left and right translation maps. These are isomorphism. Let me give you lots of examples. Okay. So lots of examples. So essentially, it's you can consider the simply example is some GLN, the field. So F is a field. Field means the F can be something like R, C, whatever. Yeah, but in this lecture, essentially R and C. It's just a matrix. Is A is n by n matrix. N by n matrix such that determinant of A is equal to not equal to 0. Okay, so it's invertible matrix. Okay. Invertible matrix. So what is the fundamental group of GL1R? Can you tell me? Oh, sorry, no, I shouldn't use GL1C. What is fundamental group? You should be able to answer. What's GL1C? What's GL1C? What? Complex number? C? Get rid of origin. Good. People just write down like this. So 0, determinant of the complex number is just complex number. So we want to have the complex number not equal to 0. Okay? So what is the fundamental group? Good. Okay. So you can compute fundamental group of GL. And then I think if you can answer this one immediately, I think you'll be genius. You're a genius. What is fundamental group? Do you know fundamental group of this one? If sorry, n is greater than 1. if you can find, if you answer this one, I think I can give you full mark, like A or A plus to you. No, but I think this is very difficult to compute. So just leave you as a homework, whatever. Just think about it by yourself. So what is the homology of GL1R? What is the homology of GL1R? Okay, zeroth element. What is this one? Homology group or GL1. It's a manifold, so you can compute homology of fundamental group and everything. R coefficient. What is this one? What is the fundamental group of this one? R plus R. What is fundamental group of GL1? It's trivial. So GL1 R is again R. Okay. So it's just origin removed. Okay. Connected components, two components. So that will get R plus R. Okay. And then whatever. So you have to pick base point to compute the fundamental group. You can either pick this base point in one component or the other component, whichever you want. It's contractible, it's trivial. So it's a manifold, okay? So one can compute any homology group fundamental group and so on. So this is GL. What's the name of GL? What's the acronym? So it's an acronym of something. What's GL? What does GL stand for? General linear group. That's called general linear group. I'm already running out of energy. So what are the fundamental group of S? Sorry. Anyway. So let me move on. So S, L, and F is the bunch of metrics such that the determinant of A is equal to 1. So what's SL stand for? Special linear. Okay, and then so this is called symplectic group. So as I mentioned in symplectic symplectic geometry, so we have something like a I already forgot the symplectic. So omega is something of sum over dpi, which dxi, I runs for 1 to n. That's the case, and then we want to find the transformation such that the omega x and y. Okay. So when x and y are the vector space of R to n. So this is the R to n is the simplex manifold. And then we just want to have the some invariance between is equal to gx and gy when g is inside of SD and R. Okay, so that's how we define the symplectic group. So you can replace R by C and so on. So that's symplectic group. So, okay, so this is the some rotation in symplectic world. Okay. Some rotation in symplectic world. And also, so also on a group, usually n is equal to, I already, okay, let's consider Bn. That is the A is Gr, and now C coefficient such that the determinant of A is equal to, sorry, no. And target A is equal to 1. Okay, and also SUM is the A is unitary group. Oh, so this is for unitary. So therefore, given a complex number, and you can have a metric that's called Hermitian metric. So given a vector B and then W, Hermitian metric is given by B dagger and W. Okay. That's Hermitian metric one can have in complex line. Okay. So this unitary group is indeed preserve this Hermitian metric. So you preserve Hermitian metric inside of C, complex number. That's called unitary group. And if you impose the determinant of A is equal to 1, this is the special unitary group. It's called special. What is the fundamental group of SU2? Trivial. Okay, trivial. I already explained fundamental group by using my belt. That's how Dirac explained. What is the homology group of SU2? Homology group of SU2. What's SU2 as a manifold? S3. What is the homology group of S3? Okay, so it's a manifold. We also have group structure, but it's a manifold. So you can compute pi and homology. Okay. You can do the same thing also on a group. What's the determinant of a unitary group? Huh? Unitary group. What's the determinant of a unitary group? Okay. And this one is indeed equal to this one, right? So therefore, it has to be equal to U1, or this is EI scalar. Okay. And if you check determinant 1, you get the special entry. OM is the same, so it becomes so let's replace O because the time is up. Becomes R, and instead of dagger, you have transpose is O, and then 1. Okay. So here you have preserved the inner product inside a standard inner product Rn. Okay. That's isometry of Rn. And this U is isometry of this Hermitian metric. Okay, let's stop here.